Hey everyone, Matthews here again, and today we're going to do a full review of AP Physics C Electricity and Magnetism. And again, this review is updated for 2025, so this year's exam, and for the future years, based on the changes College Board made last year. Okay, here are the units we're going to be going through. You can just read them off the screen. There's 6 units, and they're all about electricity and or magnetism. Let's start with the first unit, electric charges, fields, and Gauss's law. So first we need to define what electric charge and electric force is. So charge is just a fundamental property of all matter, and it's a scalar. It can either be positive or negative. Think of protons and electrons. And the magnitude of charge, of one charge, of a single electron and proton is the smallest amount of indivisible charge. So you can't divide charge further than the amount of charge that is stored in an electron or proton. A neutron is um, a neutron is a subatomic particle that has no electric charge, unlike a proton or electron. And we sometimes treat charged objects as point charges. So we ignore the size. We treat the size as negligible, the size of the charge in the context. And like charges repel, opposite charges attract. So that means the electric force can either be attractive or repulsive. And one cool thing is that the electric forces are responsible for some of the macroscopic properties like the normal force and friction. And generally, when two objects which both have mass and electric charge, the electrostatic force usually dominates on small to medium scales, but at really large scales, gravitational force will dominate since systems will be electrically neutral if they're really big. And I included the equation for the electric force here. It's equal to K Q1 Q2 over R squared, where K is a constant, which will be on the equation sheet. It's the Coulomb's constant. Q1 and Q2 are the charges of the two charges respectively. And R is the distance between the charge's center of mass, or we treat it as a point charge. So the distance between the points of the charges. Continuing on, electric permittivity is a measure of how much a medium gets polarized in the presence of an electric field. An electric polarization is defined as the induced rearrangement of electrons by an electric field. Free space has a value of electric permittivity of epsilon zero, and the permittivity of other matter is different from that of free space, and it depends on the matter's composition. Electric permittivity is related to how easily electrons can move around and change configurations. And in conductors, charges move pretty easily, unlike in insulators. So, um, on the bottom right, I include an image of a conductor and a negative charge rod. When you bring the negative charge rod close by, the electrons will move to the left end, creating a net negative charge on the left hand and a net positive charge on the right end, because the electrons are repelled by the negative charged wire or rod. And electricity obeys conservation laws. The net charge and charge distribution of a system can change due to another charge system. Induced charge separation is when the electrostatic force between two systems alters the charge distribution within the system, which results in polarization. Induced charge separation can occur in neutral systems too. The net charge of a system will remain constant unless there is a transfer of charge to or from the system. And grounding is the process of connecting a charged object to a larger neutral system. So you connect a charged disk, as I drew in the image, to the ground. So basically, electrons can either really easily go up into the disk or can go down into the ground. When electrons go into the disk, it becomes negatively charged. When electrons go down from the disk into the ground, it becomes positively charged. So when you bring a negatively charged rod close to a grounded disk, which is initially neutral, a positive charge will go up and the disk will become positive charge. So that basically just means electrons from the disk went down. Okay, now into electric fields. Electric fields originate from charged objects. And the electric field is essentially the ratio of electric force on a charge to the charge. I'll explain more later, but yeah. A test charge is a point charge of small magnitude, so its presence doesn't significantly affect an electric field in its vicinity. And positive charges feel the electric force in the same direction as the electric field. Negative charges feel the electric force in the opposite direction. And the net electric field is the vector sum of different electric fields nearby. Because of this, electric field lines go from positive to negative charges, as I drew an example of electric field lines below. Because think about it, a positive charge will be repelled from the positive charged object, but will be attracted to the negatively charged object. Okay, continuing on electric fields, in electrostatic equilibrium, the excess charge of a conductor, specifically only a conductor, will be distributed along the surface of the conductor. And because of this, the net electric field inside the conductor will be zero because the electric fields from the distributed charge all cancel out. Outside a spherical conductor, we can treat the conductor mass as being concentrated at the center. And the charge is also concentrated there too. An insulator in electrostatic equilibrium will have charge distributed throughout the interior of the insulator. And the electric field within the insulator may be non-zero, unlike a conductor. Okay, and so the previous slides assumed point charges create electric fields, but actual mass objects can create electric fields, and they're called charge distributions. So you're going to have to use symmetry to derive expressions for electric charge, and you need to know how to derive the electric fields of a ring of charge and a rod of charge. Essentially, what you're going to do is use this equation. It's the electric field equation, but in differential form. So K integral of dq over r squared, r hat. And yeah, sort of just use symmetry, see which parts of the electric field cancel out. Sometimes the vertical components cancel out, sometimes the horizontal. And you may have to put charge, like you might have to use linear charge density. So lambda equals dq dr. But yeah, now into electric flux. Electric flux is the amount of electric fields which goes through a given area. And the formula is E electric field dot A. You dot the two vectors together, or integral of E dot dA. And note that the dot product is cosine theta, Gauss's law. So a Gaussian surface is just a 3D closed surface. And what Gauss's law states is that the total electric flux only depends on the internal enclosed charge. So we can use symmetry to use Gauss's law. So use the charge density to find the total charge. And I wrote the equation on the bottom right. So essentially the flux is equal to the Q enclosed, the total charge enclosed over epsilon zero. So integral of E dot dA equals Q enclosed over epsilon zero. And usually E will be constant and dA, you can just find the area. And then you have to, generally the hard part comes when you have to find the Q enclosed. As I included on the left bottom side, you might have to use charge density, or here's volume charge density, where you have to integrate the P, the volumetric charge density with respect to volume, or you might have to use surface charge density or linear charge density or whatever. And Gauss's law is Maxwell's first equation. Okay, on to unit 2, electric potential. So first, we're going to define what electric potential energy is. The electric potential energy of a system of two point charges equals the work an external force needs to do to bring the point charges to their current position, assuming they both start infinitely far away. And the total electric potential energy of a system is the sum of the electric potential energies of each individual pair of charged objects in the system. The charges have a sign, so electric potential energy can be positive or negative. Below, I included the equation for electric potential energy, K Q1 Q2 over R, where K is just Coulomb's constant. It's on the equation sheet, and it can also be equal to 1 over 4 pi epsilon 0. Electric potential is the electric potential energy per unit charge at a certain point. So think of electric potential to electric potential energy as the same as electric field to electric force. So the electric potential due to many point charges can be determined by summing the electric potential due to each individual charge. And note that electric potential is a scalar, so it's not a vector. And a test charge can be moved between two different points to find the change in electric potential between the 2 points. So electric potential is equal to the change in electric potential energy over Q. But in integral form, it's K integral of dq over R. But for a single charge, a point charge, it can be kq over R. Continuing on electric potential energy, in calculus form, the electric potential energy is the negative integral of, sorry, the electric field is the negative integral of electric potential with respect to x. And the change in electric potential is the negative integral of electric field with respect to r or x between 2 points. Equal potential lines, or isolines, represent lines of equal electric potential. The isolines are always perpendicular to electric field vectors, meaning there's no component of an electric field along an isoline. It'll always be perpendicular. And electric field vectors always point in the direction of decreasing potential. So I drew two examples of equipotential isolines. So on the bottom left, it's two charges of the same sign, two positive charges. So notice how the equipotential lines connect. Although my drawing is bad, they should be perfectly symmetric. On the bottom right, it's two opposite charges. So note how the equipotential lines don't connect and there's a dividing line in the center. Because if the charges are different signs, it can't connect because they at no point they're going to be equal because they're opposite signs. And electric energy is conserved. It follows conservation laws. If you move a charged object between 2 points of different electric potential, it will result in a change in kinetic energy because mechanical energy will be conserved in a closed system. Change in V is the difference in electric potential between the initial and final location an object is moved from. So the change in electric potential is equal to Q multiplied by the change in electric potential difference. Sorry, the change in electric potential energy is equal to Q times the change in electric potential or electric potential difference, same thing. Okay, on to unit 3, conductors and capacitors. Okay, so we went over conductors a little bit, but now we're going to go into it in more depth. So in an ideal conductor, electrons can move freely. And notice how we mentioned earlier that a conductor in electrostatic equilibrium will have excess charges residing only on the conductor surface. A conductor with the negative charge has its electrons out on its surface. A positive charge a conductor has a lack of electrons on its surface, which creates positive charge on its surface spread out. Excess charges tend to move to the conductor's surface. And this happened in some time, but we assume that time to be very short and negligible. And a conductor in electrostatic equilibrium is an equipotential surface, meaning it has the same electric potential throughout. Because of this, the charge density on a conductor surface will be greater at points or edges compared to planar surfaces. This is just like math or logic, right? If the conductor's surface is equipotential, it has the same electric potential everywhere. Sharp places will have more charge, will have the same amount of charge, but a smaller surface area. So the charge density will be greater there compared to larger planar surfaces on the surface of the conductor. And note that the electric field within the conductor is zero, as we mentioned earlier, actually, because the net fields from the surface cancel out. Okay, now to redistribution of charge between conductors. An electric field is perpendicular to the outer surface of the conductor. A conductor can be polarized due to an external electric field, and electrostatic shielding is when the area is surrounded by a closed conducting shell, and the region inside the conductor remains free from external fields. So I included an example on the bottom right that for a conducting shell, the inside area will be shielded. When conductors are in electrical contact, charges are redistributed so the surface of each conductor are all at the same electric potential. Not the same charge, the surfaces of each conductor will be at the same electric potential. Note that the ground has zero electric potential, though it can absorb and technically provide infinite charge. And I explained grounding a few slides earlier. Okay, on to capacitors. So parallel plate capacitors have two separated parallel conducting surfaces, where each side holds an equal amount of charge with the opposite sign. The capacitance of a capacitor depends on the physical properties and relates the magnitude of charge stored on each plate to the electric potential difference created. And the electric field is constant between the two plates in a capacitor, except near the plate edges. If a capacitor is connected to a power source, a battery, then its voltage will remain constant no matter what, because that battery provides a constant potential difference. So below are the equations you need to know for capacitors. So capacitance C is the ratio of charge stored to the potential difference, which is also purely dependent. It's an internal property of the capacitor. So it's purely dependent on K, which is a constant, epsilon zero, which is the permittivity of free space, A, the area of the capacitor plate, and D, the distance between the capacitor plates. Also, for energy, the potential energy stored in a capacitor is equal to Q squared over 2C, where Q is the charge stored on a capacitor and C is the capacitance of the capacitor. And it's also equal to 1 over 2 C times the potential difference squared, which is also equal to 1 over 2 Q, the charge stored, times V, the potential difference. Okay, now into dielectrics. So if the capacitor plate separation is much smaller than the plate dimensions, the following equation that I wrote below is given from Gauss's law, which in most capacitors, the plate separation will be much smaller than the plate dimensions. So that's the electric field between is equal to Q over epsilon 0A, where Q is the charge stored on one plate over epsilon 0, the permittivity of free space multiplied by A at the bottom, the area of the capacitor plate. Now, a charged particle experiences a constant acceleration between the two plates. It doesn't matter where it is. It will always experience a constant acceleration. And a dielectric material inserted between a capacitor becomes polarized. So, yeah, you insert a material inside the capacitor, and what it does is the electric field by the polarized dielectric opposes the electric field from the capacitor. So the net electric field decreases. And if the net electric field decreases, essentially the capacitance of the capacitor will increase by a factor of kappa. So remember on the last slide, I said capacitance is equal to K epsilon 0 A over D. Kappa is the ratio by which the capacitance increases. And this happens because capacitance is also equal to Q over change in V, right? Change in V is directly proportional to electric field. So when electric field decreases, the change in V decreases, capacitance will increase. So yeah, it makes sense. And yeah, so the kappa, the factor, is the dielectric permittivity over the permittivity of free space. And it's the ratio of how much the capacitance increases by. And that's also equal to the initial electric field over the new electric field. So the new capacitance is equal to kappa times the initial capacitance. Okay, now on to Unit 4, electric circuits. First, we need to define what electric current is. So current is the rate that charge passes through a cross-sectional area. Current in a conductor consists of charge carriers traveling with an average drift velocity. An electric charge moves in response to a potential difference or an electromotive force. If the current is zero in a wire section, I wrote right, but I meant wire. That means the net motion of charges in that portion is zero too. The net motion is zero, but individual charges can still move around. Current density is defined as the flow of charge per unit area, and current density is a vector quantity. So current density, J hat, is equal to N Q, the N number of charges, Q the charge, times the drift velocity. And I current is equal to dq dt, the rate of flow of charge, which is equal to N Q VdA. So N, the number of charges, times Q, times the drift velocity, times A, which is just the same thing as the current density times the area. And current is also equal to the integral of current density dotted with the d area vector, dA. Continuing on electric current, a potential difference across a conductor creates an electric field within the conductor related to the conductor by resistivity and current density. Current can be found by integrating current density over the area. And current is a scalar, but it has a direction. No vector components and no vector addition, but it still has a direction. We say it has a direction. Conventional current is chosen to be the direction where positive charges supposedly move, but in reality, scientists discovered that it's actually electrons which are moving. So electric field is equal to P, the resistivity, multiplied by the current density. And resistivity is a process of a wire or resistor, which I will explain later. So one sec, I'm just checking. Okay, yeah. So simple circuits. So a circuit is made up of combinations of electric loops and wires and batteries, resistors, light bulbs, capacitors, inductors, switches, ammeters, or voltmeters. It can contain combinations of any of those. And charge can only flow through a closed loop. If the loop is open, charge cannot flow. A short circuit is where charges flow with no change in potential difference. So below, I included a battery. I included an example circuit, which has a battery, a resistor, a loop of wire, and a capacitor. And so from top to bottom, I also included some symbols. From top to bottom, the symbols represent a light bulb, an open switch, an ammeter, a voltmeter, and an inductor. Okay, so resistance is the measure to which an object opposes current. Resistivity, which I mentioned 2 slides earlier, is a property of a material that relates to how strongly the object opposes current. And resistivity of a conductor increases with temperature generally. Ohm's law relates current, resistance, and potential difference. It states that the current I is equal to the change in potential difference over the resistance R. Ohmic materials are materials which have a constant resistance for any current, regardless of the temperature or anything else. So resistance can be analyzed from a change in potential difference a potential difference versus current graph. So if that graph is constant, yeah, if the graph is constant, that means it's an ohmic resistor. If by constant I mean if it's linear. If it's linear, it's an ohmic resistor. Otherwise, it's not. And resistors can convert electric energy to thermal energy, which can change the temperature of the resistor and the resistor's environment. Resistance is equal to PL over A, where P is the resistivity, L is the length of a wire, and A is the area. You can also put it in calculus form as P as a function of L, dl over A, all of that integral. Electric power. So electric power is the rate at which energy is dissipated or converted by an electric circuit element. And that is power. The brightness of a light bulb increases with more power. So below I included equations of power, and you need to determine whether the current is constant or the potential difference is constant and use the appropriate equation. The power is equal to I, the current, times the change in potential difference. It's also equal to I squared, the current squared, times the resistance, or it's equal to the potential difference squared over the resistance. Okay, compound direct circuits. Circuits can be connected in series or parallel. The current through each element in a series circuit is the same. The potential difference across each path in a parallel circuit is the same. And a collection of resistors in a circuit can be treated as one resistor with an equivalent resistance. Ideal batteries have no internal resistance, and the resistance of wires can be neglected if that circuit contains other elements that have resistance. An ideal battery supplies the potential difference equal to its electromotive force, and the internal resistance of a non-ideal battery can be treated as another resistor. On the bottom right, I included examples of circuits in series and parallel. So for a circuit in series, which has any number of resistors, the equivalent resistance is the sum of all the individual resistances. So equivalent resistance just assumes that there is one resistor. So the circuit can be treated as a circuit with only one resistor, and that resistor will have a resistance of the resistance equivalent, of the equivalent resistance, sorry. And for a circuit in parallel, I included an example on the bottom, and it has two resistors, R1 and R2 in parallel, and the equivalent resistance is 1 over Req equals the sum of 1 over each individual resistance. And you can use that to find the equivalent resistance R, EQ. Okay, continuing on compound direct current circuits, ammeters measure current and must be in series with the element where current is being measured. Ideal ammeters have zero resistance. Voltmeters are used to measure an electric potential difference between 2 points in a circuit, and voltmeters must be connected in parallel with the element where current is being measured. Ideal voltmeters have infinite resistance, so no charge flows through them and disrupts the circuit. And non-ideal ammeters and non-ideal voltmeters will change the circuit properties. So here I include an image of a battery with which is not ideal. If the battery is not ideal, then we can treat it as being on the right. So it's a battery, but there's a small resistance R. That means the change in potential difference is not the electromotive force epsilon. Rather, it's epsilon minus IR, where I is the current flowing through the circuit. Okay, Kirchhoff's loop rule and junction rule. We represent energy changes in circuits by charges moving through electric potential differences within circuit elements. Kirchhoff's loop rule results from conservation of energy and states that the sum of all the potential differences across each circuit element in a closed loop is zero. We can use graphs of electric potential versus position to represent a circuit. What you do is go in the same direction as current in a circuit, or yeah, generally you try to go in the same direction as conventional current in a circuit. The battery from the negative to positive end increases the potential, and current flowing through resistors lowers the potential. Kirchhoff's junction rule relates to conservation of electric charge. That rule states that the total charge entering a junction per time equals the total charge exiting the junction per the same time. So I represented that on the bottom left. So the total sum of the current in equals the total sum of the current out. And I represented Kirchhoff's loop rule on the bottom on the other image at the bottom. So the change in electric potential energy equals Q of a charge times the change in electric potential difference that it goes through. And the sum of each electric potential difference must be zero throughout the whole circuit. Okay, RC circuits, resistor capacitor circuits. So a collection of capacitors can be treated as one capacitor with an equivalent capacitance. Capacitors in series or parallel follow the opposite patterns as resistors. That means in series, 1 over the equivalent capacitance equals the total sum of 1 over each individual capacitance. In parallel, the equivalent capacitance equals the sum of each individual capacitance. So the equivalent capacitance of capacitors connected in series is smaller than that of the smallest individual capacitor. And each capacitor in series has the same magnitude of charge on each plate. Continuing on RC circuits, you can write a differential equation for an RC circuit using Kirchhoff's loop rule. The time constant of an RC circuit relates to how quickly a capacitor will charge or discharge. And the time constant is the time in seconds for a capacitor to increase its charge from 0 to 63% of its total value, or discharge from 100% to 37% of its total value. The potential difference across the capacitor and the current in the branch of the circuit containing the capacitor both change since the capacitor is charging or discharging. And steady state is reached after a long time. So right when a capacitor is placed in a circuit, an uncharged capacitor acts like a wire and charge easily flows. So here I include an image of the differential equation for an RC circuit using Kirchhoff's loop rule. So the electromotive force from the battery equals dq dt, which is this IR of a resistance, plus Q, small q over C, where small q is the charge on the capacitor. Note that Q over C equals the potential difference across the capacitor. And you can integrate this to solve for current or charge as a function of time. And the time constant, tau, is equal to the equivalent resistance multiplied by the equivalent capacitance. Continuing in RC circuits again, as a capacitor charges, the potential difference across the capacitor changes, and that affects the charge on each plate. The current in the capacitor circuit branch and the electric potential energy in the capacitor change. All of those change as the capacitor charges. The potential difference across a capacitor, current in the capacitor branch, and electric potential energy of the capacitor all asymptotically approach steady state conditions. And after a long time, the charging capacitor will be fully charged, reaching a maximum potential difference. At this point, there is no current going through the branch with the capacitor. And when a charged capacitor begins discharging, the charge and energy stored in the capacitor both start to decrease. Charge, potential difference, and current in the capacitor's circuit branch all decrease. And charging/discharging time for times far greater than the time constant, the circuit will then reach steady state. On to Unit 5, magnetic fields and electromagnetism. Okay, so let's define what magnetic fields are. A magnetic field is a vector field which can determine the magnetic force. Magnetic fields are produced by magnetic dipoles or combinations of magnetic dipoles. Monopoles never exist, or they haven't been found yet. Magnetic dipoles always have a north and south polarity. And magnetic field lines always form closed loops. The field lines go from north to south outside, but south to north inside. And note that Maxwell's second equation will be Gauss's law for magnetism, which we'll go over later. Okay, yeah, so I included an image on the bottom. So if you split a magnet in half, you don't get one south monopole and one north monopole. You just get two south-north mono dipoles, sorry. Yeah. And so Gauss's law for magnetism is related to flux. So the closed integral of B dot dA, where B is magnetic field dotted with dA, is always equal to zero in a closed surface or in a loop because remember, magnetic fields make a full loop. They go from north to south outside and south to north inside. So they create a full loop, so the net will be zero rather than area. Continuing on magnetic fields, magnetic dipoles emerge from the circular or rotational motion of electric charges. In magnetic materials, we can think of it as the motion of electrons. Permanent magnetism and induced magnetism are properties that result from the alignment of magnetic dipoles in a system. Magnetic poles of the same polarity repel, while opposite poles attract. The magnitude of magnetic field decreases with increasing distance from the dipole, and a magnetic dipole, like a compass, when placed in a magnetic field, will align with the field. Ferromagnetic materials like iron and nickel can be permanently magnetized by an external field that causes the alignment of magnetic domains. Paramagnetic materials like aluminum and titanium interact weakly with an external magnetic field, so the dipoles do not remain aligned after the field is removed. And all objects have the property of diamagnetism, which is somewhat being magnetic. So Earth's geographic north is actually Earth's magnetic south pole, and vice versa. So a compass's north pole is attracted to the geographic north, which is the magnetic south pole. That's why a compass always points north, and we say that's the geographic north of Earth. Continuing on magnetic fields, magnetic permeability is a measure of the amount of magnetization a material experiences in response to an external magnetic field. And free space has a constant of magnetic permeability known as the vacuum permeability, mu zero, which is on the equation sheet. The permeability of matter has different values from the permeability of free space. And it depends on many factors, such like temperature, orientation, and more. Okay, so moving charges actually create magnetic fields. The magnetic field at a certain point, which is produced by the moving charge object, depends on the object's velocity and the distance between the point and object. So what you do is use the right-hand rule, point the thumb in the direction of moving charge, if positive, and the fingers curl in the direction of magnetic field. But if it's a negative moving charge, point the thumb in the opposite direction and the fingers curl in the direction of magnetic field. The magnetic field magnitude is the maximum when the velocity and position vector from the object to the point are perpendicular. And magnetic fields also exert forces on moving charge objects. You can use the right-hand rule to do this. So point your thumb in the direction that a positive charge moves. Point your pointer finger in the direction of the magnetic field, and your middle finger will point in the direction the charged object feels the force in. But note if it's a negative charge, then you have to flip it. So point your thumb in the opposite direction. Yeah, just point your thumb in the opposite direction that the charge is moving in if it's a negative charge, and keep everything else the same. And your middle finger will point in the direction that it feels the magnetic force in. So note a moving charged object can experience independent forces from both the magnetic and electric field. And the Hall effect is something you may need to know, you may be tested on, but it's when external magnetic fields cause electrons to move in a conductor, which essentially just creates a potential difference and an electric field both. So yeah, below I included the equation on the magnitude of magnetic force. on a moving charged object is just qvb sine theta, where theta is the direction between the velocity and magnetic field, which is also just q times v cross b, where v and b are the vectors. Okay, Biot-Savart's law. The Biot-Savart's law states that the magnitude and direction of a magnetic field created by electric current. It defines that. The magnetic field vectors around a segment of current-carrying wire are tangent to concentric circles centered on the wire. That means no component of the field toward, away, or parallel to the segment of the wire. A magnetic field also exerts a force on a current-carrying wire. So, Biot-Savart's law states that dB, the magnetic field created by an electric current, is equal to mu 0 4 pi I multiplied by dl cross r hat over r squared, where dl states the direction of current, of conventional current. So you have to integrate to solve this. So when you end up doing the integrations, um, you get that for a current carrying circular wire at the center, the magnetic field is equal to mu 0 I times the current in the wire over 2r, where r is the radius. Also, um, the force a current carrying wire experiences by a magnetic field is equal to integral of I times dl cross b hat, where dl is the direction of current in the wire. So that current carrying wire, that's the force it experiences from an external magnetic field. Okay, Ampere's law. Ampere's law relates the magnitude of magnetic field to the current closed by an Amperian loop. Solenoids, or a helical coil, are assumed to be very long with uniform magnetic fields inside the solenoids and negligible magnetic fields out of the solenoid. An Amperian loop is a closed path around a part of a current carrying conductor. So we can create our own Amperian loops. The net magnetic field at a point can be created by combinations of current carrying conductors, loops, and more. So Maxwell's fourth equation is Ampere's law with Maxwell's addition. And Maxwell's addition is just changing electric fields create um, changing electric fields create magnetic fields too. So yeah, Ampere's law is the closed integral of B dot dl is equal to mu 0 times the current enclosed. So when you use this law, the magnetic field from a solenoid is equal to mu 0 times n, the number of, I believe it's the number of total turns in the solenoid. I may be incorrect. It might be the density of turns multiplied by I. But yeah, it'll be on the equation sheet for sure. Actually, let me check that right now, just in case it's on the equation sheet. Okay, so let's see. Yes, it's on the equation sheet, and the n over there represents the number of loops per unit length. Okay, so the magnetic field from a solenoid is mu 0 ni, where n is the number of loops per unit length. Yeah, okay. And yeah, so you can use Ampere's law, and for a long current carrying wire, the magnetic field generated by the wire varies with mu 0 I over 2 pi r. Okay, final unit, unit 6, electromagnetic induction. Sorry. Okay, so we mentioned magnetic flux earlier, but magnetic flux can be defined for a magnetic field through a perpendicular area vector outward from a closed surface. And the sign of flux is given by the dot product between the magnetic field and the area vector. So it's B dot A, or integral of B dot dA. Electromagnetic induction. So Faraday's law describes the relationship between a changing magnetic flux and the resulting induced electromotive force. So to determine if the area or magnetic field is constant or none at all, that's what we use it for. So EMF can also be induced in a long solenoid, and the total induced EMF is the EMF in one loop multiplied by the number of loops. Lenz's law is another law that states an induced EMF generates a current that creates a magnetic field that opposes the change in magnetic flux. So you have to use the right-hand rule for that. Lenz's law comes from like sort of conservation of energy. Well, not really conservation of energy, but just the universe, like infinite energy is not possible. So it can't like support the change in magnetic flux. It has to oppose it. So Faraday's law is that the induced EMF is equal to the negative time derivative of magnetic flux, which is equal to negative d b dot a over dt. And the absolute value of the EMF produced by a solenoid is n, the number of loops, times the induced EMF from one solenoid. Or sorry, not one solenoid, one loop of the solenoid multiplied by the number of loops. So continuing on, Maxwell's third equation is Faraday's law of induction, which we defined on the previous slide. Oh, actually, never mind. Faraday's law of induction, which is sort of similar to what we defined on the previous slide, but it's more specifically with the changing magnetic flux and an induced electric field. So Maxwell's equations showed that electric and magnetic fields follow wave equations, and that electromagnetic waves travel at a constant speed in free space. So the EMF is equal to the integral of E dot dl, which is equal to the negative d flux dt, which is, yeah, basically what we said on the other slide, but related to E dot dl. And the speed c is 1 over the square root of epsilon 0 multiplied by mu 0. Okay, so induced currents and magnetic forces. When an induced current is created in a conductive loop, the present magnetic field exerts a magnetic force on the charge carriers in the loop. Magnetic forces are only exerted on the loop segments that are within the external magnetic field, and these magnetic forces can cause translational or rotational acceleration. The force on a conducting loop is proportional to the induced current, which depends on the rate of change of magnetic flux, resistance of the loop, and velocity of the loop. And Newton's second law can also be applied here. So yeah, we put this equation earlier, but magnetic force on a current carrying wire or loop is integral of I dl cross B. Inductance is a conductor's tendency to oppose a change in current. And the inductance depends on the conductor's physical properties. So straight wires have zero inductance. A solenoid has significant inductance, and we model the inductance of a solenoid with an equation. Inductors also store energy in the magnetic field generated by current in the inductor. The energy stored in the magnetic field generated by an inductor, where current flows, can be dissipated through a resistor or used to charge a capacitor. So the inductance of a solenoid is equal to mu core n squared A over L. And the electric potential energy of a solenoid is 1 over 2 Li squared. Continuing on inductance, the transfer of energy generated in an inductor to other forms allow conservation laws. And Faraday's law can be applied to an inductor, which is the induced EMF from an inductor is equal to minus L di dt. So earlier we did circuits with resistors and capacitors. We can also do circuits with resistors and inductors, or LR circuits. A resistor dissipates energy stored in an inductor as the current changes. And Kirchhoff's loop rule can be applied to a series LR circuit. That loop rule will just be E, the EMF, is equal to IR plus L di dt, where E is the voltage EMF. The time constant for an LR circuit is a measure of how quickly an LR circuit reaches steady state, similar to an RC circuit, but tau is equal to L over R equivalent. And the time constant is the time for the current in an inductor to reach around 63% of its final asymptotic value, assuming it starts from zero initial current. And it's the same thing. If it starts with an initial current, it'll reach 37% of its initial value. Yeah. So continuing on LR circuits, when a switch is initially opened or closed in a circuit with an inductor, the induced EMF will be equal and opposite in direction to the applied potential difference across the inductor branch. The potential difference across resistor current in the inductor and energy stored in the inductor are exponential with respect to time and have asymptotes. After a long time after the time constant of the circuit, the inductor will act as a conducting wire with zero resistance. And below, I drew an example of what an inductor will look like in a circuit diagram. There are also LC circuits with capacitors and inductors. In circuits with only a charged capacitor and an inductor, the max current in the inductor can be solved using energy conservation in the circuit. So in LC circuits, time dependence can be modeled as simple harmonic motion. Note that it's technically not simple harmonic motion, just that the charging/discharging of the capacitor can be modeled as SHM. So when we write that in equation form, it'll be d squared, the second derivative of q with respect to time, so d squared q over dt squared equals minus I LC over q, where omega, the angular frequency of the modeling as SHM, is equal to 1 over the square root of LC. That's it for the video. Thanks for watching. Let me know if you have any questions at all in the comments below. And yeah, this course is pretty hard. Be sure to practice a lot. It must be stressful with the new year, but you all got it. Best of luck.